Hi everyone, today we're going to look at section 4.3 exponential functions. And start the PowerPoint. Alright, so an exponential function has the form f of x equals c times a to the x. Here are the conditions. A has to be greater than 0, so positive number. It cannot be equal to 1, and c, your constant, cannot be equal to 0, and it's a real number. So the c represents your initial value, and the a is your growth factor, your exponential growth factor. And then x is in the exponent, that's your variable obviously, and f of x is the same thing as y, so that's your output, your dependent variable. The ratio of consecutive outputs in an exponential function is constant. So remember, the word ratio means the fraction. So what you'll be doing is checking the ratio between consecutive outputs to make sure that it's always the same, and that will tell you that you do in fact have an exponential function. Alright, so the first question is linear or exponential. So what we want to do is look at our y values. Our x values are stepping up by 1, so we can look just at our y values. If you look at these, the change between them to get from 5 to 2 and from 2 to -1, from -1 to -4, the pattern there is to subtract 3 every time. From -4 to -7, same thing, subtracting 3 every time. So this is an average rate of change of -3. And if you remember from earlier in the course, when you have a constant rate of change, that means that you do have a linear function. Okay, so you're looking for addition or subtraction with the same pattern between the y values for a linear function. Okay, take a look at the next one. The x values are still stepping up by 1. The y values, however, have a different type of pattern. What we want to look at here is the ratio of the consecutive outputs. So I'm going to take like the second y value and put it over the first one. 16 divided by 32, that reduces to 1/2. Same thing here, 16 and 8, when I compare those, 8 over 16, that reduces to 1/2. 4 over 8, that reduces to 1/2. 2 over 4, same thing. So all of these ratios, when I reduce them, reduce to 1/2. So here the ratio of consecutive outputs is always 1/2. The ratio of the consecutive outputs is 1/2, which means that this is an exponential function by definition. Okay, another way to look at that would be that to get the next y value, you can multiply your previous answer by 1/2. So I can do 32 times 1/2 to get 16, 16 times 1/2 to get 8, 8 times 1/2 to get 4, and so forth and so on. You could also check the differences between these, but you'll see that they're not constant. So if you did like 16 minus 32, 8 minus 16, 4 minus 8, all of those would have different rates of change. So you would know by doing that that it's not linear. All right, the next thing that we want to look at is the graph of just a basic exponential function. We'll do kind of a simple one. F of x equals 2 to the x. Pen's not calibrated very well here. Okay, so f of x equals 2 to the x. If you're following my original form here, c times a to the x. In this one, my c is 1, my a is 2. So there's like an understood 1 right here. You could write this as 1 times 2 to the x. All right, so to graph this, let's just make a table. Just plug in some positive and negative x values, pretty small, to see what's going on here. Okay, so if I plug in negative 2 right here where I see x, that will be the exponent, 2 to the negative second power. So this will be 1 over 2 to the positive second power, if you remember your exponent rules, which is 1 over 4. If I plug in negative 1, that will be 1 over 2, so 1/2. 2 to the 0, which is 1, right? Anything to the 0 power is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. So that's plugging in the x values in the table right here for the exponent. All right, now let's take a look at the graph. All right, so if I plug in negative 2, I got 1/4. Let's see, go ahead and count up to 8. 3, 4, 5, 6, 7, 8. So negative 2 has a y value of 1/4. Negative 1 has a y value of 1/2. 0, 1. 1, 2. 2, 4. 3, 8. Now you can see that it's going up pretty quickly. All right, so if I connect these, this will have an arrow because I could plug in larger x values. This will also have an arrow because I could continue to plug in smaller x values. All right, so now let's look at the properties of this graph. First, we'll look at the domain. Remember, domain means what x values am I allowed to have? And the answer here is everything. I can plug in any x value for that exponent. So from negative infinity to infinity is included in my domain. The range, that's what y values can I have? That would be starting here at the x-axis and going up from there. There's no way to get negative answers, so it would be from 0 to infinity, not including 0, so you do have regular parentheses on your 0 here. Okay, the y-intercept, where it crosses the y-axis. That would be the point 0, 1. And you'll see that that point shows up on a lot of exponential graphs because when you raise anything to the 0 power, you get 1. All right, the horizontal asymptote here, there is one at y equals 0. So right on that x-axis. Here on this end, you're getting closer and closer to the x-axis, but never touching it. All right, this graph is also smooth and continuous. So you can draw it without picking up your pencil. Ooh, sorry, the tablet's not doing too good. Okay, so smooth and continuous, all in those first 2 quadrants, arrows on both ends. The one I've drawn here is kind of in general for a being greater than 1. Here I've used a equals 2, but this is generally what it looks like for a being greater than 1, and it is always increasing. All right, the next one we'll look at will be with an a of 1/2, so a between 0 and 1. Okay, so similar graph here. 1/2 raised to the x. So your c is still 1. That would be right here. This one is still going to have that same y-intercept of 0, 1, but it will be always decreasing. So same sort of shape, but decreasing from left to right. So when your a is between 0 and 1, so here my a is 1/2, you'll have the same sort of shape, but it's always decreasing. All right, let's also remember our shifting rules from, I believe it's 1.5 in the textbook. So, haven't been doing a good job numbering, but this will be number 3. Directions are to sketch the graph. So here's my function. 2 to the negative x minus 3. So I'm going to base this on the graph of 2 to the x, the first graph that I drew, and then do the transformations. So the stretching, the flipping, up, down, left, and right, all of that. Okay, so first let's just write out what the transformations would be. This negative in front of the exponent right here, or in other words, replacing x with negative x, is going to cause me to reflect over the y-axis. Okay, then after that, subtracting 3 off the end of the function will move my graph down 3 units. Okay, so we'll kind of do this one step at a time. I'll do it very roughly here. So this graph is 2 to the x, the first one that we graphed. And then if I reflect that over the y-axis, now it will be decreasing instead of increasing. So that is 2 to the negative x. And then from there, using that one, I can shift down 3 units. One way to do that is to use just your y-intercept point at 0, 1 and move that down 3 units. So 1, 2, 3. Now that point will be at 0, negative 2, which means the asymptote would be 1 more unit down from that at negative 3. Okay, still same shape, decreasing from left to right. So this one is 2 to the x minus 3. Okay, so same sort of shifting rules that we've done for every other family of functions. You can go back and review those. I believe it's in 1.5 in your textbook. All right, I'm going to go ahead and stop this presentation right here, and we'll pick up with solving exponential equations in a separate PowerPoint, even though it's still part of the same section.